Talk about it? It's a very sensitive topic. We have no shortage of that at my house right now. There's shit everywhere. No, sorry. So, did this surprise you that the effect here was positive and not negative? That means the intercept, let's take a look at the intercept. Intercept for, whoa, back this thing up. The intercept for non-gamblers is 1.0 or 1.729. That's right here. 1.729. Beta was 0.892. So we add these together and we get like 2.61 or so is the intercept for non-gamblers. That means if your gambling factor is at 0, and remember we set the mean of the gambling factor to 0 for identification. That means if you're a 0 level gambler at a gambling factor, you're not, and you're a non-student, you're going to have a very close to disagree endorsement, whereas a student has a yeah, sure, why not endorsement. I you know how it makes sense of this? A lot of these students, to them, money is just haven't had a lot of it yet, don't know how to handle it. To me, that's what I'd say. Yeah, I'll go back another day. If I lost money, I'll go win it back. Like to me, if I lose money one day, I'm not only not going back, I'm kicking myself. That's money. I could have gotten more out of the warmth of setting it on fire. Right? I could have created like warmth out of that. But that's just my, you know how that works again. And listen, I'm a man who stayed a number of nights in Vegas, some of which were somewhat unplanned because the night previous to leaving went so well. But you know, I'm no stranger to setting my money on fire. But point being, maybe that's the explanation I would. Anyone want to add on anything about that? Could also be that the students really didn't take the survey seriously. I'm totally legit with that. We've compelled them into how many hours? 6? 11 for one semester of class? Or total?
11 credits and a half hours, 1 credit.
Oh my goodness. In one semester. Oh my gosh. Yeah, this is why. Yeah, I'll go back another day. Boom. The most well-studied population of people who are like, oh, the hell, I'm going to give you my data. Love it. Anyway, so yeah, isn't that somewhat interesting? But now we can interpret all this. What is the, if we were to keep going with this, what's the slope for this GRI3? Well, that's the factor loading, the gambling slope right here. 1.088. That means for every 1 unit more of gambling, the expected response goes up 1 more unit. So for every 1 unit higher on the gambling factor, people essentially pick a higher up category to rate the item with. So people who are like super gamblers and have like 6 point higher than mean would be like, yes, I endorse this item. I strongly agree with going back to win my money back. So, strategy. Questions? How does this sit with your knowledge so far? Does this seem pretty straightforward? Or are you like, whoa, this stuff is crazy. I haven't seen that before. Seem pretty legit?
Did you test these questions? Did they test the questions before?
No. Oh, well, yeah, sort of, but just not on the student population. This was not a good survey. It has lots of problems. But yeah. So what is then the question? We were interested in really is the effect of being a student on gambling, right? So is there a mean difference between students and non-students on the gambling factor? So we look at this regression slope just like we would if this were observed variables. We see the p-value is small, so it's significant, and we see that being a student means you have a mean gambling factor score that is 1.293 points lower as an unstandardized effect. If we were to go and standardize this, really what that means is that take a look at std.lv, that term right there. We don't want to standardize the student variable because it's a categorical variable. Dividing it by standard deviations doesn't make much sense. But what this tells us is that students are on average 2 standard deviations, or 2.018 standard deviations lower than non-students when it comes to the gambling factor. And that is what I would expect for students. We wouldn't expect them to be a population of people who may have used NCAA brackets here or there, or bought a lottery ticket here or there in their life with limited resources for money, probably aren't going to be super gamblers, right? So, all right. So everything that you would talk about in this analysis would come from that result. It's just that result now is where we look. Right? We don't need to come up with a gambling sum score. We don't need to come up with a gambling factor score. We don't need to do 2 analyses. We just do it once, get a result, publish on it. Publish it would say students are study finds students significantly lower than in their attitudes towards gambling or something like that. Okay, here's our path diagram. Oh, isn't that pretty? R codes the negative weighted things as red, and the positive things as green, which sort of seems to bias. Like red means stop and green means go. But I don't know. I guess you had to pick colors, right? Could just be the person who did that likes the holidays, likes Christmas colors. I don't know of any sports teams. Does anyone know any sports teams that are green and red? It's one combo you never see. It'd be awesome.
Milwaukee Bucks are green and red.
Oh, that's right. Yeah, that's right. Yeah, they have a pretty intricate court these days. It looks pretty neat. All right. So, what's that?
I think Free State High School is the same.
Free State. Oh, that's right. That's right. Yeah, Free State. Here I go. 2 quick examples right off the top of your head.
They're changing their colors anyway, so they're.
Oh, the Bucks are really? Oh. Oh, all right. They've changed their color several times, though, right? So, I've actually seen a game. Is it still the Cole Center that they play in, or no? Was it Bradley Center now? Ah, okay. They're going to stay in Milwaukee. That's good. All right. So here is our model implied covariance and our our normalized residuals from it. The key in structural equation models is that the part that we're doing here, we took the factor analysis part, and it kind of governed this part of the covariance matrix, which is the items that measure the factor. And with the exception of that direct effect, which was right here, right? Now, the weird thing about a structural equation model is that the part that's this off diagonal here does not have any direct effects by default to it, although we added one because of our big normalized residual. And so where the misfit shows up in these types of models are on all these items and their covariance between the things that are not part of the factor model and that you're using these exogenous variables that might be out there or endogenous variables that might be out there, because there's nothing in the model that can go spill over onto them to describe these covariances. And so I put this in capital letters down there. That's where everything starts to blow up. It's those off diagonal terms. If you've got the measurement model working, and for the most part it fits really well, then it won't change a whole lot. Usually, although sometimes it does, when you add something, this part right here. It's this off diagonal, it's the big pain right here. That thing. So we struggle with it very frequently. By adding that direct effect, this is the normalized residual. This is the direct effect we added between student and GRI3. You see that we made it so that we have no residual left. It fits perfectly with what it should be. Questions? Oh, wrong one. Let's keep going then. So here is the overall form, and I actually agree with Billy on this one. I prefer the equations more than I do the picture because the equations give me all the effects that may show up. But what we end up having in this structural equation model are like two parts. It's like an overall path model, but there's a measurement part and there's a structural part. And in the measurement portion, bless you, you see the indicators of the factor analysis show up here on the left-hand side, and then we have our factor show up on all of those. And we can put the actual other predictors of these on, right? We can have this type of analysis. And in the structural model portion, that's usually the other path analyses that show up. And this is in the case here where we have a gambling factor that shows up there, just like it was a variable itself. So all interpretations, though, everything that you've learned about regression hold, right? So that's nice. At least that holds. R squared. This is nice also. It can tell us what proportion of the variance in the gambling factor is due to student status or whatever we're predicting it with. So we described 39.2% of variation, right? Being a student or not describes that. Now, here's where I wanted to talk a little bit about that question about marker items. Remember, marker items is where we estimate the factor variance. And that's what happened in our model. We have a factor variance estimated, and you'll see it right here. Gambling's variance is estimated at 0.25 versus the standardized factor. The standardized factor makes this factor variance estimate equal to 1, but then it makes it so that we estimate up here all loadings are estimated. Right? So we could do that. The model fit will be identical. It's just now what we interpret in our parameters starts to go haywire. And it goes haywire because this gambling factor, this variance right here, is smaller than it would be if we had the same model but didn't have the direct effect of student predicting gambling. Right? It's a residual variance. It's smaller. So by fixing it, if we had the standardized factor, it would be 1 in both of those, even though in the latter, when we predict it, it should be smaller. Something's got to give, and it's the other parameters of the model that give in that situation. So let me just show you what ends up happening. Where did it go? So on the left here is the prediction. These are the two analyses with. This is marker item analyses. And this is the model where we take, this is kind of the precursor model, the prediction, the model without predicting gambling directly, right? This is what the factor variance of gambling would have been if it was not a residual. It's just 0.408. That's how much variance there is in the factor period. And then when we put the value in, it goes down to 0.250, and it tells us our R square went from 0 to 0.392. We described none of it. Now we're describing 39% of its variation. Now take a look at, this is the standardized factor identification. This is where we set the factor variance to 1 in both of these, right? So again, the model fit is identical to the previous slide. These two numbers will check out to be the same as on the slide prior to it. Negative 5570.85 or 865. Oh my goodness, I did it again, Templin. I do this every week. Two things that are constant in class. It's Google. I'm asking Google, and I'm hitting the button that takes me all the way to the beginning because evidently if I hit 2 of the arrow buttons simultaneously, it takes me home. I missed my hit. Anyway, the marker item log likelihood for without predicting gambling is negative 5570.865. With the standardized factor, it's the same, negative 5570.865. Same thing with the prediction of it, same log likelihood, negative 5399.671, 5399.671. So what I'm getting at here is the model is identical. These are the same models. Take a look at what happens to the parameters, though. The variances are fixed. Our gambling now, we're still describing 39% of the variation. The factor loadings now, take a look at those. They shrink. The item intercepts get a little bit crazier. The residual variances are roughly the same. Here, you see slight changes in some of the parameters, but not nearly as bad. So this is kind of the rationale for why in structural equation models we do marker items more often than standardized factors. We can always get the solution from the standardized factor. If we wanted the standardized factor solution, we could just look in this column right here, std.lv. That gives us what would have been had we gone and standardized things. But in this context, when we go and put the standardized factor in, when we force it, we can't get back to the unstandardized version. So now, if you're only building a CFA model, to just build a CFA model to either validate some instrument or quantitatively assess its fit, it doesn't really matter. 6 of one, half dozen of the other. It's in the context where your factors may be predicted by things that really changes things. Weird? Questions? For those of you struggling with this, I've been in your shoes. I struggled with it for years. In fact, when I learned things in grad school, we didn't do anything with marker items. It was all standardized factors. And then I got here, actually. It was here on this campus, and I saw people doing the marker items all over the place, and I thought, well, I should probably learn this. And yes, they are the same model. It's just interpretation. And sometimes when models break. Questions? All right. So, issues in building structural equation model. There are multiple ways that models can show misfits. So it's tough. It's tough to build a structural equation model from the get-go and get it to work without tweaking things to get the model fit to work. The current practice, what you read in textbooks, says that you should build the measurement models first and then put them into your structural equation model, and I agree with that. But you'll see some type of questionable advice given in some textbooks. So some people will say, and I don't know if the chapters I gave you advise this or not, can't remember, but use just identified measurement models, right? That's measurement models with 3 indicators, like we did here. They will say it gives you fewer degrees of freedom where misfit can happen. That's their rationale for it. And it's true. But why I think it's bad is there's poor reliability, and actually beyond that, it's poor validity for any latent construct. And remember, a latent construct is just, it's composed of the items that build it. There's nothing that says you can't name it anything you want to, but that name is really going to be the thing that becomes the life of it. Right? I could have called this latent variable anything. I called it gambling, and that's really a misnomer. But I could have called it I don't know, something amazing and published and whatever else. But no, it's just there's nothing that says it's gambling. It's now whatever those 3 items are doing simultaneously. Sometimes you will read to build measurement models with structural equation models simultaneously. I would actually say that's not necessarily all that bad. But they would say the full calibration can lead to better overall model fit. And it's true, but the problem with building them simultaneously, and this is why a bad idea, I would say, is that a lot of times the choices that you'll make about your measurement model should be in the context of that measurement model. Right, there's nothing about predicting gambling that allow us to change the items of our survey to make it fit any differently. Right? Sometimes you might see us drop items from a survey when we start predicting it with a factor. And really, if you think about what that measurement model is, that's the thing you're trying to build. That's why you have the survey in the first place. So building it first, even if it still brings out bad fit, and by itself helps. And measurement models, in this case, building the 1-factor model, and if you have multiple factors, building that on top, and then putting them into the structural equation model is kind of the place to go. And then finally, the other part that people will say is, well, we'll just do a 2-stage analysis. Do your measurement model, see that it fits, take either the factor scores, which in psychology and the social science, we don't use factor scores. In education, we use them all the time. In fact, your GRE is a factor score. Right? Or we take a sum score, and we use that, and in the place of the circle in our structural equation model, we now have a box that represents the sum score. So if I were to go back in time here, what that would do is sometimes you'll see people go and say, well, I fit this measurement model. I saw that it fit, so now I'm just going to cancel it out, and I'm going to put a box here that's now gambling. And that box is represented by the sum of all three of those items, just the sum score. All right, and I'm just going to predict it as if it were a box. This is the path analysis example that we started class with. Right, each one of those was a latent variable. And if you go a step further, that's what's always done. Am I wrong? I mean, like, if you look at like any journal, 99% of the time we just take a sum score and put it in, right? Okay. It could be wrong, and where it could be wrong, it's a bad idea. It's not necessarily wrong, but it just makes more assumptions than you can hold, right? The biggest part of it is that you propagate error, right? You take things that have variation in certain ways, and you shut down the variation, right? Instead of giving somebody this construct that you can't observe, so you say, I know I can observe it, and this is exactly it, rather than saying I got a factor score, or it's got this. I'm not sure if it's, there's variation in all sorts. But anyway, that's really going to be the topic of the next class. I'm going to put it out there to you that I'm going to put it out there. I'm going to provoke you a little bit here. I love giving talks at conferences where I say, the world is wrong, and then try to show why it is. No, or try to say something controversial at first. And then everybody hates me at first. Try to be like the in wrestling, the heel, get the crowd against you at first and then sort of bring you over to your side. Say something that people don't think to try to broaden that horizon a little bit. Like, is this wrong? Everybody's doing it. Could everybody be doing it wrong? Is it a bad idea? What could happen? So we'll talk about that more next time. Actually, I'll show you a little bit of it now. Had we done the previous analysis without structural equation modeling, I'm going to take that last bullet and add to it, right? Let's do what everybody else does. My mom always used to tell me, what, if your friends jump off a bridge, are you going to jump off a bridge with them, right? Because I would always say, yeah, but Mom, they're doing it. You ever had those conversations with your parents or with your children? You know what I'm talking about? I put my parents through hell. And they're just, my dad's passed on, but my mom, I think somewhere, she won't say this to me, but somewhere in the back of her mind, she's like, oh, that's your turn. So we'll see. Yeah, I heard that a lot. Anyway, the previous analysis was built under the guise that I want to show you kind of the way it works when everything works out beautifully. Sometimes it doesn't work out beautifully. You've got to do something different. But let's just go into the world where we take that, what we would have done. We said, oh, yeah, we have this one-factor model of gambling. It fits the one-factor model. Let's just make a sum score with it and plug it into our analysis. What happens? What changes? All right? The bigger picture of why we use SEM is that gambling does not exist. All right? We have three items that purport to measure it. All right? Do they actually measure them? Well, that's where CFA comes in line. If we're already going to do a CFA, why don't we just go a step further and do an SEM, right? But without saying. Without SEM, we could take the similar analysis by using the sum score of the three gambling items. Right? And I'd say that likely that's more prevalent. That's always what we do, right? So we're going to have the potential for biased estimates, so our regression slopes will be different. And this part right here, this first one, the bias of regression slopes, that's fairly common knowledge. That's the rationale given for SEM, the attenuation due to measurement error, attenuated correlations and so forth. I don't know if you've heard this before. The second part is, I think also very problematic, is that the standard errors may be biased. Right? We take something that has variance and say, no, it doesn't have any variance. We'll just shut that thing off. It's like saying we have a lot more information about our data than we really do. And when we see in those situations, we see them in other contexts and models as well. Multi-level models, for instance. Sometimes people will go and fit regression models to different groups of people and then take the regression slopes and do secondary analysis with those. Sometimes that's called a slopes as outcomes analysis. That has problems in that the error in the regression slopes, not every regression slope is estimated perfectly. There's error in each one of those, becomes problematic, it leads to type 1 error rate. So in other contexts, in other fields, this is really well known about bias and type 1 error rate when it comes to shutting off things with error or variance. I don't know that it's as well known in psychometrics. I seem to not have that discussion. I have this discussion often. There's a lot of feelings in the world. In fact, a social psychologist who will remain nameless in my previous department, I probably told you this story, but I'll say it again. We figured this stuff out 50 years ago. Things haven't changed in 50 years. That's why we, see that quant programs don't exist anymore. Well, we tell you you're doing it wrong, and the right way to do it's a lot harder. Well, we don't need to do that. We'll just keep doing it this way, right? We really have a great marketing campaign. Where do we sign up, right? If I can get published without doing it, anyway. It's more the idea of knowing what you're getting into when you do it, knowing where the assumptions are, and knowing what's bad and what's not. So I did that. I know I ran a sum score analysis. Actually, here, I'll tell you the truth. My name is Jonathan, and I've done this before. I've put sum scores into analyses. In fact, I've even done some in this class. See the path analysis lecture, right? Happens. But let's talk about what happens with it. It's not what we should be doing. And it's as I've gotten into this a little bit more, like everybody should floss. You hear that? Do you floss your teeth? Yeah, but really, I mean, like every day, like every one of them. It's a lot. It's a lot of flossing, right? Right? So, I mean, like every study, every one of them? Yeah, kind of, right? Anyway, I created the sum score, and this is called GRI 135 sum. Truth in advertising. Item 1 plus item 3 plus item 5. That's it. And, take a look at that. I calculated its reliability. We haven't talked about reliability yet in this class. We're going to talk about it in the next lecture 2 weeks from now. Right? The alpha, believe it or not, this alpha, a lot of times people call it Cronbach's alpha. Gutman-Cronbach is what I'm calling it. I believe Gutman had come up with it first, and then Cronbach rediscovered it. Anyway, that value for these data was 0.352. We could actually come up with the Cronbach alpha as a combination of our factor loadings and unique variances. Isn't that cool? It implies a very specific statistical model. And if we have a statistical model that applies, we can check model fit. We can tell whether or not it works. So how about that? Break down your alpha feelings. Devane, you have a look to you. How am I supposed to? It tells you how often I use that alpha. Anyway, sorry. Questions? So, 0.352. Would you ever use that in an assessment? Never. Terrible. Case in point, a 3-item measurement model has terrible reliability. But let's do it anyway, shall we? Yeah. Actually, here, this is the model that gave me the Gutman-Cronbach alpha. If you want to go see my R syntax for it, you can estimate it in R directly in it. You'll see the model doesn't fit well. Anyway, so here's our sum score model. Right there. It's just a simple linear regression. So now I'm going to take a look at the comparison of the standardized coefficient, right? So what we're looking at here, this is a huge eraser, my goodness. All right, so what we're looking at, we have this gambling factor and we were predicting it with student. And we're looking at this beta weight right here. And what we need to realize is that student, this thing is 0 and 1, always. But the gambling factor, sometimes it's the estimated variance of gambling as a latent variable. And sometimes it's the estimated variance of the sum score that we just created. And these variances are going to be very different. So to compare these estimates on the same scale, we're going to make it so their variances are 1, or we're going to standardize the coefficients. And so to do that, we don't want to standardize the student variable. We only want to standardize with respect to the latent variable variance. That's what where this std.nox syntax in Lavon or R comes from. Standardized solution, std nox. It standardizes this thing in this regression model and makes the variance of it 1, but it does not standardize the student. So this tells us the slope when we do the sum score is negative 1.273. Right? That says for every students are 1.273 standard deviations smaller on their gambling sum score. Right? And it tells us the standard error is 0.119. Now let's compare that result to the best model that we ran, the model that had the mimic model. Now, here's the thing about that sum score. Right? We put the 3 variables together, we added them up, we predicted them. Do you remember what happened when we did that in the latent variable context? Our first model broke because we needed that prediction of gambling on one of the variables itself. If we just use the sum score, we can't tell that we need that. And that's telling us, oh, we made an assumption that the means for these are the same. It's problematic. But if we use the mimic model, which is not really the fair comparison, we really should use a model that's no mimic, that doesn't fit well. But if we used it, here, take a look at the difference in these estimates. Our model said that students were 2 standard deviations lower. The sum score model said that they were 1.273 standard deviations lower. So if you're thinking about this in a null hypothesis testing situation, it's a bias towards 0. It's downwardly biased, right? So this is a fairly big common phenomenon. This is the attenuation for lack of range or whatever it is, truncation. These are attenuated scores. It's causing this attenuated, this is attenuated. But now take a look at the standard error though. 0.119 versus 0.177. In the sum score model, it looks like we have less error. And that's because we've taken things that have variation and said, no variation here. These things are fixed entities. Now, if we really want to take a look at the valid comparison, it's this bottom one, and that's where you see the biggest difference in standard error. Right? It's like half the standard error for the sum score. Right? Now remember, the standard error is important because it's the denominator in the z statistic. And in both of these cases, we would actually conclude the same thing. There's a significant difference. Now the magnitude would be different, but we wouldn't change the result. But you can see what's happening, right? If the z is farther away from 0, then we're more likely to reject the null hypothesis. What goes into z? Standard error. Right? And if the sum score model shrinks the standard error, it's more likely to have a bigger z, which is more likely to give us a null rejection. Now the question would be, is that rejection a type 1 error or not? And in this situation, it doesn't look like it's type 1 error because the right models are saying it's fine. It's just we're now all of a sudden leaving ourselves open to critique or chance or whatever. There's been a lot of noise lately about the replicability of research. Have you heard about this? Have you seen this, talked about it? It's a big deal. There's a lot of social science research that's been found to be not replicable. And people are talking about why. Right? I actually think part of it has to do with the psychometrics here. Right? We're taking things that have error and shutting the error off. So we're getting type 1 error rates. We're seeing things that should be 0 claim to be non-zero. Not the case here. Another context. You have enough of these studies, you're going to see it. And so all of a sudden we're having all these findings that may not be true show up. So there. I'm on my soapbox. I'm pitching to you what that big deal is. But that's the reason why we're doing psychometrics in the first place is measurement error. Let's get to the finish line here. We're a step away. And so 2 weeks from now we're going to talk about what to do when you can't do the SEM version of it. Right? Not just don't do it, it's bad. It's all right, let's fix it. What can we do then? And I've got a few suggestions or ways to make it work. Believe it or not, those might be even harder to publish. So not only is it easier, not only are you more likely to get a significant effect, not all the time can you do it. Oh, wait, where do I sign up? Yet again, quantitative science telling you, really, if I ever motivated you to use the method to the path, boy, that's it. Questions on this? Attack my logic. Let's go. I want to have a debate about this. I actually would love a debate about this with some of other faculty as well, too. It's an interesting finding. Quant faculty, for that matter. I don't know that I'd find some faculty that would... maybe there'd be a few that disagree with me over here in our program. My friends... No, I wouldn't. Wait, I don't have any friends. No. I think Billy and I actually see eye to eye on this. This is why we do... By the way, this is another reason, so this is only with 3 items, so the impact of non-reliability is huge here. But if you have a survey where you have reliability of 0.9, 0.95, you're not going to see this big impact. It may be close enough to call it good. So this is kind of an extreme example. Anyway, there we go. Talked about it. Questions? All right, real-world analysis here. I'm actually not that far from the end. Mind if we just push on through to the end here instead of taking another break? Get done early today. You okay with that? You want another hour? Am I ripping you off? I can look up Google things for you for an hour. Bad idea. Okay, I took an example of academic progress from a large university in a state that is supposed to be for lovers. Anybody from the East Coast? Virginia? Virginia's for lovers. Anybody from Virginia? I've heard that. I've seen the bumper stickers. I think I've only been to Arlington. No, I mean I don't go to the Northeast very often, and Virginia's not the Northeast. So, but you know, occasionally because of business, I got to go to D.C. and sometimes that really means Arlington, right? So.
Cemeteries are for lovers.
Oh, that's right. I hear the rest of the state's wonderful, but I don't have the data, so I couldn't rerun the analyses. These were data from a colleague that used to work there or does work there or something like that. Can't give you too much information. Now, here's an interesting thing. I just ripped on some scores, and we're sort of going to use them. But I'm going to trick it a little bit. This is a hopefully less egregious form of a sum score, but we'll see. I took the students at this large southeastern or mid-Atlantic university were subjected to testing every year. They're very big on whether or not their curricula for undergraduate studies is effective at teaching students what they're learning. And you'll see this. Actually, at our university and our state, people are pushing for this as well. Are students learning what we're teaching them in college? And that's a really good question. We hope they would be, right? Well, this place actually shuts down for a day or two each semester to do testing for each curriculum. And one of those was to do mathematics testing. And so the first year when students are freshmen, they take the first testing day, they take a kind of a math pretest. It's all sorts of math that shows up in college curricula. And then a couple years later, they take a math post-test. And now here, these scores on this pretest are, each item is scored in correct or incorrect, and they just add them together. And we get a Gutman-Kronbach without an H, reliability of 0.81. So, hey, who's the reliability czar in this class? Jennifer, you're already our model fit czar and doodling czar. But anyone want to anoint themselves king or queen of reliability? Lou? Would you think this is good reliability? All right, Lou says, Lou, you are now the reliable. Would you prefer a type like czar, queen, goddess? I mean, does something work? What's that? Whatever of reliability is, Lou, and it's 0.81. Sorry, Lou. Thank you for playing along. I don't mean to embarrass you. I just mean to make the class a little more fun. This stuff is not fun usually, so even for those who teach it. I mean, I love it, but I just come on. So that's the pretest. That's when they get to college, and then I believe it's their senior year or 2 years after 2 years in the university. So in theory, they go through their undergraduate, their lower level math courses. They're now juniors. They're taking their upper level stuff. They take the same form of a math test. I actually think it's the same items. It says, all right. And now we've got a pretest and a post-test. We want to see if there's a difference. But this math test is built off of all sorts of undergraduate math, and there's a big variation. Like if you're like me when you started college, you were in remedial math, Right? If you're like a lot of kids who start college who are like engineering majors, they've already done calculus. They don't need that anymore. They're up to linear algebra. They're up to other things. So there could be a very big effect of certain courses on mathematics. And in fact, there are 29 courses the university had identified that were related to math and science. So the question is, does the course impact, or better yet, perhaps even mediate the relationship between the pretest and the post-test? Huh? There's a structural equation model for you. So here are some questions that the people who were doing the self-assessment at the university had thought. Do the scores improve on the post-test when compared with the pretest? Does coursework significantly affect post-test scores? Did the score on the pretest predict the coursework the students took? So if you scored poorly, were you more likely to, no thanks, I'm not going over there? And did coursework mediate the relationship between the pretest and the post-test? All right. So because of the nature of the data, we had several modeling issues that were problematic with SEM. We're going to use something called this. We're going to take the sum score, but we're going to do something to sort of identify what error is in it. All right. So a sum score has both variance due to the trait plus variance due to measurement error in it. And so the total variation of the sum score, if you remember classical test theory, right? Sometimes we say that a sum score, sometimes we'll call it X. Actually, I'll just call this the sum score is equal to, you've seen this equation, the sum score is equal to true score plus error. And if you want to see what the variation of sum score happens to be, well, the variance of true score and error are uncorrelated, so it's the sum of variance of true score plus variance of error. And using classical test theory, we actually could trick this out. We could actually say, what is the variance of error? It happens to be variance of true score minus variance of sum score total. But really, we can show that the formula is 1 minus the reliability times the variance. Actually, the variance of the sum score, right there. Okay. Have you seen this before? Heard this? Variance of error. It's how we bound in classical test theory. Have you put confidence intervals around your true score or your test scores before? Anyone done that? It's how we get our standard error of measurement. Right, it's the same for everybody. Okay, so this is not crazy stuff. What I'm going to do then is take the box that is the sum score, and I'm going to put a factor on it that represents the trait. Right? But I'm going to say, hey, the variance of this sum score really gets split between the factor and the actual error. What's left, this thing, is 1 minus reliability times the variance of the sum score. Right here. Right? Since I know the reliability and I know the variance of the sum score, I can sort of trick this out. Now, I still have estimation error that I'm collapsing over, which is problematic, but this is the closest thing. It's one of these tricks I can do to try to bring measurement error to it. So what does that mean the factor variance happens to be? It happens to be what's left over, or what this happens to be rho times the sum score. Variance right there. You seen this before? This is what's called a single indicator model. If I do this and I constrain the factor loading to 1, right, I actually have identified all the parameters in this analysis. I've compartmentalized or partitioned my measurement error. And I still have estimation error, so that may be a problem if I have a small sample size, but measurement error at least is partitioned. And now I can treat this factor score as if it's a factor in an analysis. So that's what this is called. It's called a single indicator model. I believe Brown's textbook talks about this in some of the chapters. I don't know if you saw those in what you had read, or if you flip through it. This is what's called a single indicator model. So each of the courses is binary, and it's hard to include them in an analysis where they're binary. So we actually had to trick the analysis out as well too. So let me see if I can do this. So we created 3 coursework factors. right? Which was, we took 3 segments of these math classes, and we said, if you took these classes, you're more high on this type of math, and these classes, you're higher on this type, and vice versa. So, not a great strategy. This is M+ syntax. Let me get to the results here. What did you... How to do, again, same process. We built syntax, we estimated the model. This is where we actually fix some of the parameters to constants. We have normalized residuals. And this is our model right here. Okay, so we have a pretest factor. It's a single indicator, so this is the pretest. This is the standard error of measurement of the pretest. It's not estimated, that's why the zeros are there. We fixed the factor loading, so what we're end up doing is actually estimating the factor variance right here. Fix the factor mean. And then from that, what we're doing is predicting the number of courses they took in each of these 3 areas. Because M+ has its limitations as well. Really, I'd like to put these as categorical mediators, but M+ throws up at you if you do. My program for DLM doesn't. But M+ does. For those of you who do DLM, this is DLM right here. This is our learning map. Anyway, so what this is doing is the pretest has no effect on which type of courses you're taking, it's saying. Here's the post-test. The post-test is also a single indicator, and it's saying it has a significant. You can predict the post-test pretty significantly. But then for each of the courses that you take, some of those have significant, let's see here. That one, and that one are the 3 paths to say what does the sum of the, for every one more course you took in this area, do you have a better score on the post-test? And all 3 of those are non-significant as well. So indirectly, and then you have those undirected arrows, those are all the correlations of the things in the middle. But this is another path diagram. Essentially what we've done is treat some things as observed, some things as latent in quotes, although it's latent because they're single indicators. Still not the ideal, but it's a step closer. And from this we're learning that we really don't do a good job. We can do indirect and direct effects for everything. The total indirect effect, for instance, from pretest to post-test is minuscule. It's nearly 0, which means pretest is not predicting which courses you're taking, or those courses are not predicting what the post-test happens to be. So scores. So answering those questions from this SEM analysis, yes, post-test scores improved by 0.6 standard deviations for every 1 standard deviation in pretest score. So by the way, this is one one final model that we're answering all of our questions with. That's the other thing about this modeling approach. You want to do it all from one thing. The more that you have multiple models, the harder it is to get the right information. Does not mean it's impossible, it's just a lot harder. Did coursework significantly affect the post-test scores? The answer is no. How'd you like that as a university administrator? You give students a pretest and a post-test. Post-test scores grow. The coursework is not related to it. What's happening? All right. Good question. Did the score on the pretest predict the coursework students took? Actually, yes. G1, which was an area of difficult math, was reduced. Looked like there was a small significant result. It's questionable, weak result. So took 1 less standard deviation number of courses for it, and there was no mediational relationship. So I'm flying through this. Questions on all of this. So why did I do this as a structural equation model? Well, I was trying to find an example. And dang it, wouldn't you know that there's not a lot of structural equation modeling data that are good examples out there. Mainly because it's either hard to do or not frequently done. So I hope what I'm doing is providing food for thought, though. Right? It's food for thought for me for quite a bit. Right? What's the harm in doing things without SEM? What I want you to think about. I think it's awesome, by the way. Come if you have critiques, if you have thoughts about this, is awesome. And what's the harm in doing SEM? So when you come to class 2 weeks from now, I'll talk about the sum score analysis a little bit more, the assumptions it holds, what a sum score is, how does that compare to other types of scores you might get, like a factor score. Right? Here's one for you. The sum score has a perfect correlation with the factor score. When you hold all the loadings to be equal and all the residual variances to be equal. That's interesting too, right? Okay. So the ultimate question in all of this is the trade-off between how long or how hard is it going to be get my software to work to do things the right way. I can see eyebrows raised, is that right? Right? Versus how much is it going to hurt me if I'm doing it that way. So I'm going to try to take a less preachy approach. I want to take more of an agnostic approach, but do realize what's happening with it, right? If you are an informed consumer and say, well, yeah, that's a limitation from software, that's one thing. But if you don't know that and then later on go on and, well, I can show you quotes from testing companies that don't know this. Right? These are people who are paid to know that. So I want to do that. So I'm going to stop here. That was my concluding remarks. Do you have questions? So next week, no class. Use that time for whatever. But in 2 weeks, bring your critiques, bring your rebuttals, bring everything. I like it. I don't feel like I think like a good debate is good, and there's an interesting juxtaposition between what we're about to learn in the course and what happens in reality. So if you have a good grounding in reality, which I don't, bring it. I want to talk about it. Bring it. Oh, let's fight. No, we're not going to this is not a psychometric brawl. This is more just let's talk about it. So thanks everybody. Adios. Have a good week.
Can I grab you a little quick?
Just a moment.
Yeah.